So next, let us discuss how to work with more complicated potentials. So in real life, potentials are continuous objects and they don't have the nice neat form that we saw for the finite potential well. So for example, suppose we have a potential which has this form. So this is our x-axis and this is our potential. And suppose the potential does something like this. And we are interested in some energy which is less than the highest value of the potential. So energy is roughly something like this. So for such potential, what we can do is that we can approximate it by a more step-like potential. So we can approximate such a potential by saying that this potential is crudely represented by something where we have a steep potential here, and then a step here, and then another step here, and say another step here. And that we are looking for some solution where the energy eigenvalue is roughly something like this. So how do we solve for such a potential? So let's make an observation. And the observation is that we know that both psi and psi prime have to be continuous, and that in this region, psi is a sinusoid. So let's take psi. Let's take a form of psi. Psi in general will have some form where it'll have an amplitude, and it'll be some sine of given by k of x times phi, and k squared is up to some constant is the kinetic energy. So if I take the derivative of psi, then the derivative of psi will be given by a times k cosine of kx plus phi. Now if I eliminate from, so if I take these two equations and then I eliminate the sine and cosine from them, then what do I get? I get a is equal to psi squared plus, let me call this thing m because that's a slope, and then it's going to be m squared divided by k squared, and the whole thing is square root. Now since psi is continuous and m is continuous, as we go across this potential steps, what will happen is that both this thing and this thing will be continuous, but the kinetic energy k is given by 2m e minus v divided by h squared. But this thing is not continuous, it jumps over here. And therefore, k squared is not continuous across the jumps, and therefore A is not going to be continuous across the jumps. Moreover, we see that the kinetic energy here is much bigger than the kinetic energy here because it's given by the difference of these two guys. And we saw that whenever the kinetic energy is large, the A is smaller. And when the kinetic energy is small, A is larger, the amplitude is larger. And not only that, we can also see that, from this solution is that, whenever the kinetic energy is large, the wavelength is small. And when the kinetic energy is small, the wavelength is large. Why is that? Because remember that k is related to the wavelength by 2 pi by lambda. So they're inversely proportional to each other. So having made these observations, we can now sketch what the wave function will be for this thing, for this potential. It'll be some exponentially decaying thing. And once we get into in region 1, sinusoid, which will be rapidly oscillating, but it's amplitude won't be that big, but once it gets to the smaller kinetic energy region, the amplitude will be bigger, but the sinusoid it'll have a longer wavelength. So it'll be something like this. So this is how we can qualitatively figure out what the wave function is for potential which have several steps. What about potential which are continuously changing? What if I have a potential, which is roughly given by something like this? So in this region, the potential is continuously changing. To figure this out, what we need to do is that we need to approximate our continuously changing potential by a series of steps. And then we use the intuition that we developed before, which is when we have less kinetic energy, we have longer wavelengths, and when we have less kinetic energy, the amplitude also is larger. So for this thing, we can have our wave function will be something like given by, so it'll be continuously changing. So here the wavelength is smaller, here the wavelength is larger, here the amplitude is smaller, here the amplitude is larger.